This video will be a brief history of acids and bases. We'll start off with the ancient Greeks and Romans, so this is prior to 476 AD. The Greeks loved the idea of a simplified universe. They were brilliant ancient scholars, but their desire to simplify concepts and show that the world is perfectly balanced sometimes held them back, as they oversimplified concepts that were more complex. For instance, they classified compounds according to taste, and there were four categories: bitter, sweet, sour, and salty. This knowledge was passed on to the Romans, who started to refer to sour substances as acidic. This comes from the Latin word acidus, for sour. Bases were less well known at this time, and a known base was a mix of ash and animal fat, which made soap. Bases were recognized as substances that could neutralize acids, and this sort of fit with this Greek desire for balance and harmony. At this stage, bases were called alkalis, which came from the Arabic word for roasting. We still use the term alkali today, but it doesn't encompass all bases. You've probably heard of the term alchemy, which was most prevalent between the 7th and 17th century AD. However, it's proposed that alchemists originated in ancient Egypt, so prior to the 7th century. The word alchemy is likely derived from the ancient Egyptian word chem, which referred to the fertility of plains near the Nile. Esoterically, chem referred to the dark mystery of the first matter. Alchemists thought that this first matter carried the seeds of all existing things, from the past and present to everything that will exist in the future. This sort of shows the distinction between ancient alchemists and modern chemists. Both studied matter, but alchemy had this mystical aspect to it, which was obviously left behind as science progressed. So the word chem moved from ancient Egypt through Greece and eventually became the term alchemia in the Arabic world, and this meant the art of transformation. And it is this word that alchemy is derived from, and by default, the word chemistry comes from this background as well. So alchemy was the ancient study of matter with the aim of creating more valuable substances, curing diseases, and extending life. It was based on the idea that any form of matter could be transformed into any other form of matter. Obviously, this was false, and that's why many alchemy experiments failed. Famously, the experiments tried by many alchemists to turn cheap metals into gold. Alchemy moved through the Golden Age of Islam and the Renaissance period, and it's this period where acids and bases were further studied. So properties of substances including hydrochloric acid, ammonia, sulfuric acid, and acetic acid were studied by alchemists during these periods. Jumping forward a little bit, in 1300, a Spanish scholar, Arnaldus de Villanova, extracted a compound from a lichen, and that's this plant over to the right. And he used this compound to test substances for acidity. This compound we call litmus, and it's now used in litmus paper to distinguish acidic substances and basic substances. Robert Boyle, who was an Anglo-Irish philosopher, he extended this work by developing some of the first acid-base indicators, which could not only determine whether something was acidic or basic, but start to measure how acidic or how basic a substance was. And he is known as the father of modern chemistry because he performed experiments under controlled conditions. He's also quite famous for developing gas laws. Okay, let's jump ahead to Antoine Lavoisier. He was a French chemist who first attempted to classify elements, and this led to a more systematic analysis of acids and bases. At this stage, bases were defined as substances that could neutralize acids to form a water and salt, so much closer to our current understanding. Lavoisier developed the first theory of acids, and the theory proposed that all acids contained oxygen and that acids are oxides of a nonmetal combined with water. Now, Humphrey Davy, who was a British scientist, later showed that this theory didn't work because acids like hydrochloric acid and prussic acid do not have oxygen. So the theory was disproved, And this is an example of the falsification of an idea when it cannot be applied in all cases, which is an essential aspect of the scientific process. Our understanding evolves as new discoveries are made, and sometimes old theories are disproven. Sometimes they are instead built upon or adapted to encompass a larger range for the concept being discussed. Which leads us to Svante Arrhenius. So he developed the ionic theory of acids, and this theory stated that acids are substances that dissociate in aqueous solutions and produce hydrogen ions. And I have protons in brackets there. So let's sort of talk about how can we call a hydrogen ion a proton? Well, here we have a hydrogen atom, and it's worth noting here that hydrogen has three isotopes. There's the hydrogen atom, which has no neutron, deuterium, which has one neutron, and tritium, which has two neutrons. So if we're talking about hydrogen, we're referring to the isotope with no neutrons. So if we ionize this atom by removing the electron, it becomes the hydrogen ion, and you can see in the diagram that all is left is a proton. And that's why we can refer to hydrogen ions as protons. So the ionic theory states that in aqueous solutions, hydrogen ions combine with water molecules to form hydronium ions. An Arrhenius acid increases the concentration of hydrogen ions in water, and an Arrhenius base increases the concentration of hydroxide ions in water. Let's have a look at examples, starting with acids. Here we have hydrochloric acid, which dissociates in water to form hydrogen ions and chloride ions. So it can be seen that we have an increased concentration of hydrogen ions that form from an acid. And here we have a base. We've got sodium hydroxide, and it dissociates in water to form sodium ions and hydroxide ions. And you can see that we have an increased concentration of the hydroxide ions when this base is in an aqueous solution. Now, this was extended to explain that if you combine acids and bases together, they cancel each other out. So essentially, you can see the sodium and chloride ions join together to form a salt, and the hydrogen ions form water with the hydroxide ions. So the concentration of hydrogen ions and hydroxide ions both dissipate because water is formed when the two combine. Now, we'll talk a little bit more about this first statement. This is called a neutralization reaction because it's neutralized the acidic and basic properties of the aqueous solution. So in an aqueous solution, the hydrogen ions don't stay as hydrogen ions. They immediately react with water to form hydronium ions, and they do it like this. So a more accurate equation to represent what's happening when hydrochloric acid dissociates in water is this reaction here, where we've got hydrochloric acid plus water becoming hydronium ions plus chloride ions. Now, in practice, chemists talk about the concentration of hydrogen ions and hydronium ions interchangeably. And so either this reaction, which is more accurate, or the reaction on the previous slide, which is simpler, is acceptable to depict what's happening here. Now, Arrhenius developed this theory, but it was not well received until 1903. And it was in 1903 that he received a Nobel Prize in chemistry, and today there is a building at Stockholm University named after him. However, this theory is now considered too limited in application because it cannot be generalized beyond aqueous solutions. So we needed a theory that could encompass the behavior of acids and bases in non-aqueous solvents and to molecules in the gas phase, which leads us to Bronsted and Lowry. In 1923, Bronsted and Lowry independently extended the ionic theory. So the Arrhenius theory of acids and bases was not necessarily disproved, but it was extended to encompass a bigger range of acid and base situations. And so Bronsted and Lowry were not working together. Bronsted was Danish and Lowry was English, but they were working on the same thing and discovered the same thing around the same time. Now, historically, when this happens, it's led to ethical questions around who should be credited or or should the credit be shared. In this case, the theory was named after both scientists and they were both credited. And in the modern age, peer review process in science aims to ensure credit is correctly awarded to those responsible for discovery. So the theory states that an acid is a substance that can donate a proton and a base is a substance that can accept a proton. Under this definition, water, which is neutral in the ionic theory, can act as either an acid or a base and is said to be amphiprotic. So let's have a look at an example. Here we have a hydrochloric acid combining with water to form the hydronium ion and the chloride ion. So the same reaction as the previous slide, but now we're going to classify each substance as an acid or a base, depending on whether it's donating or accepting a proton. So hydrochloric acid is an acid because it donates this proton, so the hydrogen ion, and it becomes this base, so a chloride ion. And water in this case is a base because it accepts that proton from hydrochloric acid and forms the hydronium ion. Now, you'll notice this double arrow here. We can also classify the two substances on this side of the reaction, and we're going to look at what happens to them if we were to do the reaction in reverse. So the hydronium ion is classified as an acid because it will donate its proton and become water, and the chloride ion is classified as a base because it will accept a proton and become hydrochloric acid. Another example here, but in this case, water is an acid because it donates a proton and it forms the hydroxide ion. Now, we'll need to talk about conjugate acids and bases. When an acid loses a proton, it forms a base, and this is known as the conjugate base, and together they are a conjugate acid-base pair. So here you can see that hydrochloric acid will form chloride ion. So this is the conjugate acid-base pair. The conjugate acid for water is the hydronium ion. If water is acting as an acid, then the conjugate base is the hydroxide ion. So amphiprotic substances like water on the previous page can act as a proton donor and a proton acceptor. And the term amphiprotic comes from the Greek word amphoteros, meaning both. And this prefix amphi is also used in amphibians to describe animals that live in both land and water. So we've talked about water that can act as an acid and a base, and I have depicted both reactions here. It is worth noting that amphiprotic does not have the same meaning as amphoteric. So amphoteric substances can act as both an acid and a base, including reactions that do not involve the transfer of a proton. So that means that amphiprotic substances are also amphoteric, but the converse is not always true. So amphoteric substances are not always amphiprotic. And for an example, aluminium oxide is amphoteric because it reacts with both acids and alkalis, but it is not amphiprotic. And this amphoteric nature is explained by the Lewis theory, not the Bronsted-Lowry theory. But that will be explained in another video.